All right, today we're going to try something different. This paper just came out of Anthropic. So this is scaling monosemanticity, extracting interpretable features from Clone 3 Sonnet. And this is pretty exciting because it feels like this is going to be an important work for interpretability in large language models. It kind of reminds me of the time when in convolutional neural networks, there was this paper, I can't remember the name now, that demonstrated for the first time that different layers of the convolutional net turn out to sort of operate at more and more high-level visual features. So like the first layer was looking for lines, the second layer was looking for, junctions, and the third layer and so on. Eventually you get to like layer that neurons that look for things like cat faces and wheels of vehicles and stuff like this. So that paper kind of kicked off this interpretability streak of work in convolutional neural nets, and it was super useful. And it feels like this might be a similar thing for large language models. Now, this paper just came out a few hours ago, so I haven't read it yet, and I don't really know whether this is exactly what it's going to be, but it feels like it. So I thought instead of reading through it and then having a 5-minute overview, I will just try reading through it live, and we'll spend about an hour reading through it and talking about it, and then we'll figure out if it's interesting. So basically, what they do is they come up with, they have some way of finding features, and these features are meaningful combinations of, I guess, neurons. This is very hand-wavy, very high level. But they come up with these features which are semantically meaningful. And then they realize that these features are both interpretable. So basically, the way I think about these features is that each feature is a collection of, let's just call them neurons for now, in the network. So they find that the features that are related to a specific thing get activated when that specific thing is being sort of processed or thought about. But also, interestingly, they can affect the output of the model by manually sort of putting emphasis or de-emphasizing these features. And there are a few examples. So the example here is that given a prompt like, I came up with a new saying, if you basically turn the knob that's responsible for the sycophantic praise feature, you will get an output that's like gushing praise for whatever you say. And I have more interesting examples like that. But that means that that's a good signal that these features are actually meaningful in the way that we think about it and like lend themselves to making these models interpretable. And this is building on earlier work from, I think, 8 months ago. It was pretty popular at the time, this earlier work, when it came out. And it was really interesting, but it was operating in a much smaller scale. It was kind of a toy model. And here they're working with Cloud 3 Sonnet, which is a really powerful model. It's not the biggest one, it's not Opus, but it is basically like GPT 3.5. It's better than 3.5. And that's great. That's a frontier model, one of the best ones out there right now. And it turns out that even at this huge scale, you can do useful interpretability work. So that's the background. Let's read through the paper. So that's basically what I just said. They work on Sonnet. This is another example. So they find the diversity of highly abstract features. So it means that the features are kind of interpretable. They both respond and behaviorally cause abstract behaviors. So another example they were showing is that this feature only activates this feature about Golden Gate Bridge activates both for images of Golden Gate Bridge, but also for text mentioning Golden Gate Bridge. So they have this multimodal space that maps both text and images, and in both cases, the same feature gets activated. So again, and also different languages. So again, this is a promising sign that they're really onto something here. Of course, this is the interpretability team, so they care about safety. So a lot of this work is going to be about how much of this can be sort of used for safety work. So let's go through the key results. Sparse autoencoders produce interpretable features for large models. So we knew this part. I think this paper is basically proving that this part is also true. Scaling laws can be used to guide the training of sparse autoencoders. So scaling laws is basically like the more that you need to train more to get more data, to get more performance. And this also applies here. The resulting features are highly abstract, multilingual, multimodal, generalizing between concrete and abstract references. So cool. That means that it's something that is useful for interpretability. There appears to be a systematic relationship between the frequency of concepts and the dictionary size needed to resolve features for them. Not sure what this means yet. We'll probably get to it. So dictionary learning is what they sort of described in the earlier work, and we'll cover that as we go through the article. Features can be used to steer large models to, for example, influence behavior, as we mentioned. We observe features related to a broad range of safety concerns, including deception, sycophancy, bias, and dangerous content. Cool. So, scaling dictionary learning to Claude 3 Sonnet. Our general approach to understanding Claude 3 Sonnet is based on the linear representation hypothesis and the superposition hypothesis. So both of these were covered in the earlier work with the toy model. At a high level, the linear representation hypothesis suggests that neural networks represent meaningful concepts, which we refer to as features here, as directions in their activation spaces. The superposition hypothesis accepts the idea of linear representation and further hypothesizes that neural networks use the existence of almost orthogonal directions in high-dimensional space to represent more features than there are dimensions. Right, so this is this figure from the original work where they had, I don't know if I can pull this up, but this was kind of interesting. Let's see if we can... Is this going to be the right reference? Yes, this is what I was looking for. Okay, I lost the figure. So this is the figure I was looking for. So here they're saying you have the two-dimensional space, and naively you could represent it. You could use it to represent two different concepts, like the x-axis is one concept and the y-axis is a different concept. But they actually find that, I mean, it's not a novel finding, but the fact that large language models use this kind of property was kind of novel. So the property specifically is that in this two-dimensional space, you can represent 5 different concepts, for example, and you can represent less or more, and there are different trade-offs. But let's say you stick with 5, so you have 5 dots here, and basically different spots on this plane have different distances to different concepts. So then if you're over here, you know that you're kind of close to this concept. If you're over here, you know that you're close to this concept. So instead of just going X and Y, you can kind of, do like almost like a nearest neighbor search. And importantly, these things are kind of orthogonal. So the network basically learns to arrange these concepts in a way to be useful. And the trade-off here is that, yes, instead of 2 dimensions, you can now do 5, but you're trading off some accuracy, right? Because things are now sort of easier to blend together. And also these things are not completely independent. So like these two things are just geometrically, they need to be related. If you have something here that's kind of in between these two, and that's not always what you want. If you just had completely orthogonal features like say X and Y, that's not a problem. The more dimensions you add to this low dimensional space, the more of a problem this will become. So this was basically the linear representation and superposition hypotheses. If one believes these hypotheses, the natural approach is to use a standard method called dictionary learning. Recently, several papers have suggested that this can be quite effective for transformer language models. In particular, a specific approximation of dictionary learning called a sparse autoencoder appears to be very effective. To date, these efforts have been on relatively small language models by the standard model foundation models. Our previous paper, which focused, so there was like a Slate Star Codex article about this, and it became pretty popular in Hacker News pretty cool, interesting work. A previous paper which focused on a one-layer model was a particularly interesting example of this. As a result, an important question has been hanging. Will these methods work for large models? Or is there some reason, whether pragmatic questions of engineering or more fundamental differences in how large models operate, that will mean these efforts can generalize? This context motivates our project of scaling sparse autoencoders to Claude 3 Sonnet, Topic's medium-sized production model. The rest of the section will review a general sparse autoencoder setup. The specifics of the 3 sparse autoencoders will analyze in this paper, and how we use scaling those to make informed decisions about the design of our sparse autoencoders. From there, we'll dive into analyzing the features our sparse encoders learn and the interesting properties of Claude 3 Sonnet they reveal. Before we go through this, let's just have a look at the table of contents, because one trick I kind of learned while reading a bunch of papers is that it might be sometimes easier to skip through a bunch of sections rather than just reading linearly. So we were about to read this section, and we will. But before that, let's look at what else is there. So assessing feature interpretability. So once you find a feature, how do they prove that the features are actually useful, interpretable? Then they look at a bunch of features and look at the neighborhoods and are they complete and so on. Features as computational intermediates. I don't know what this is yet. We'll find out. Searching for specific features, and then a bunch of investigation about safety-relevant features. Again, this is the interpretability team, which whose mandate is to look at safety and interpretability. So this is unsurprisingly a big section. So just quickly, there are code features that are safety-related. There's stuff about bias and sycophancy, deception, power-seeking, manipulation. There's a case study, something about criminal dangerous content, features relating to models' presentation of self. That would be really interesting. And comparison to other approaches. And then there's discussion and related work. So before we jump into this, let's go to discussion. That is often a sort of a trick to take a shortcut and figure out what the paper is basically trying to say, what is the interpretability of all of this, and then we can go through a bunch more detail. So what does this mean for safety? It's natural to wonder what these results mean for safety of large language models. We caution against inferring too much from these preliminary results. Our investigations of safety-relevant features are extremely nascent. It seems likely our understanding will evolve rapidly in the coming months. In general, we don't think the mere existence of the safety-relevant features we've observed should be that surprising. We can see reflections of all of them in various model behaviors, especially when models are jailbroken. And they're all features we should expect pre-training on a diverse data mixture to incentivize. The model has surely been exposed to countless stories of humans betraying each other, of sycophantic yes-men, killer robots, and so on. This is interesting. So we can see reflections of all of them in various model behaviors, especially when. So I think, like, the way I understand it is that by clever prompt engineering and prompt hacking, you can kind of induce the model, guide it towards putting emphasis on some of these features that they discover here. And that was pretty much what I think people suspected until now, but it's all a black box, and you have to outsource your jailbreaking work to like millions of anime characters on Twitter so they can figure out how to jailbreak your model. And now we can start to be a little bit more principled rather than throwing everything at the wall and seeing what sticks in terms of prompt engineering, how to guide models to do these things that we want or not want. Now, with these features, we can actually guide the model in a more targeted way. So that's really cool. Instead, the more interesting question is, when do these features activate? Going forwards, we're particularly interested in studying what features activate on tokens we'd expect to signify Claude's self-identity. I wonder what this means, what they mean with self-identity. Some potential claim: Claude's self-identity includes elements identifying with a wide range of fictional AIs, including trace amounts of identification with violent ones. So this is like not something they actually claim, but it's something that they would like to investigate. That would be cool. And yeah, that's really cool and really interesting. What features need to activate or remain inactive for Claude to give advice on producing chemical, biological, radiological, or nuclear weapons? So obviously they want to make the model safe, and they don't want the models to teach people how to make nuclear weapons. What features activate when we ask questions probing codes, goals, and values? So I can imagine that if you do this work and you, for example, realize that the feature responsible for connected to deception activates more frequently than you thought, that will be kind of suspicious. What features activate during jailbreaks? Just like I mentioned, like investigating how jailbreaks interact with these different features would be really interesting. What features activate when Claude is trained to be a sleeper agent? So that was another work that they were doing as well. I think it came out of Anthropic too. How do these features relate to the linear probe directions already identified that predict harmful behavior from such an agent? What features activate when we ask Claude questions about subjective experience? Can we use the feature basis to detect when fine-tuning the model increases the likelihood of undesirable behaviors? Interesting. Okay. Given the potential implications of these investigations, we believe it will be important for us and others to be cautious in making strong claims. We want to think carefully about several potential shortcomings of our methodology, including illusions from suboptimal dictionary learning, such as messy feature splitting. For example, one could imagine some results changing if different sets of fine-grained concepts relating to AI or dishonesty get grouped together into SAE features in different ways. Okay, I don't really understand what this means right now. I will need to read more about dictionary learning, but it is always nice to see discussion of limitations. So this is something we'll have to look into. So basically, if dictionary learning is not the right thing, or maybe not optimally set up, the features might be less useful than they would otherwise be. Cases where the downstream effects of features diverge from what we might expect given their activation patterns. Okay, so this is like we found a feature and we think it is something because it seems like it's interpretable this way. But actually it's doing something else that we're kind of missing. I think that is the translation of this potential shortcoming. We have not seen evidence of either of those potential failure modes, but these are just a few examples, and in general, we want to keep an open mind as to possible ways we could be misled. I wonder how many layers of this there is. Like, is it possible for a model to try to pretend to have a feature or to expose a feature when it is trying to mislead it? I don't think that's possible today, but maybe at some point with more complicated models it would be. But it seems hard to believe. Generalization and safety. One hope for interpretability is that it can be a kind of test set for safety, which allows us to tell whether models that appear safe during training will actually be safe during deployment. In order for interpretability to give us any confidence in this, we need to know that our analysis will hold off distribution. Right. This is especially true if we want to use interpretability analysis as part of an affirmative safety case at some point in the future. So what does this mean? We need to know that analysis will hold off distribution. Yes, so they're looking at the features, how they're looking at the features using the sort of data they know about. But if they get off distribution data, so the kind of data they haven't seen before, are these features still useful for interpretability? Makes sense. Especially true if we want to use interpretability analysis as part of an affirmative safety case. Okay, so yeah, okay, that makes sense. In the course of this project, we observed two properties of our features that seem like cause for optimism. Generalization to image activations. Our SAE features were trained purely on text activations. Image activations are in some sense dramatically off distribution for the SAE, and yet it successfully generalized this to them. So I wonder if they do, how they do multimodal embeddings. Concrete abstract generalization. We observe that features often respond to both abstract discussion and concrete examples of a concept. For instance, the security vulnerability feature responds to both abstract discussion of security vulnerabilities as well as specific security vulnerabilities in actual code. Thus, we might hope that as long as our SAE training distribution includes abstract discussion of safety concerns, we'll catch specific instantiations. These observations are very preliminary, and as with all connections to safety in this paper, we caution against inferring too much from it. Limitations, challenges, open problems. Our work has many limitations. Some of these are superficial limitations relating to this work being early, but others are deeply fundamental challenges that require novel research to address. So, superficial limitations. In this work, we perform dictionary learning over activations sampled from text-only datasets similar to parts of our pre-training distribution, and did not include any human-assisted formatted data that we fine-tuned Claude to operate on, and did not include any images. In the future, we'd like to include data more representative of the distribution Claude is fine-tuned to operate on. On the other hand, the fact that this method works when trained on such different distribution seems like a positive sign. Again, I really wonder if they're doing something like Clip, but they must be. Because I guess if they trained only on images, that means they must have some way of putting images in the same embedding space as text. So they must be doing something like Clip or something like that. Inability to evaluate. In most machine learning research, one has a principle that objective functions can be optimized, but in this work, it really isn't clear what the ground truth objective is. That's very true. The objective to optimize, a combination of reconstruction accuracy and sparsity, is only a proxy for what we really are interested in, which is interpretability. For example, it isn't clear how we should trade off between the mean squared error and sparsity, nor how we know if we made that trade-off. As a result, while we can very scientifically study how to measure the loss of SAEs and inverse scaling loss, it's unclear that they're really getting at the fundamental thing we care about. How many of those are there? Cross-layer superposition, a few more. Okay. We believe that many features in large language models are in cross-layer superposition, and gradient descent often doesn't really care exactly which layer a feature is implemented in, or even if it's added in a specific layer, allowing the features to be smeared across layers. Interesting. This is a big challenge for dictionary learning, and we don't yet know how to solve it. This work tries to partially sidestep it by focusing on the residual stream, which, as the sum of the outputs of all previous layers, we expect to suffer less from cross-layer superposition. Concretely, even if features are represented in cross-layer superposition, their activations all get added together in a residual stream, so fitting in SAE on a residual stream layer X may suffice to disentangle any cross-layer superposition among earlier layers. Unfortunately, we don't think this fully avoids the problem. Features which are partly represented by later layers will still be possible to properly interpret. I believe this issue is very fundamental. In particular, we would ideally like to do pre-post transcoder style SAEs for the MLP, and especially challenging. Okay, I don't get most of it. You probably need to know what SAEs are in detail. I'm sure we'll get to it. But I mean, kind of high level makes sense. There's a fundamental limitation of how they're looking at building the features and interpreting them, and it doesn't apply sometimes. So it's a limited view on what the network is doing, and they might be missing some information. Getting all the features and compute, we don't believe we have found anywhere near all the features that exist in Sonnet, even if we restrict ourselves to the middle layer we focused on. We don't have an estimate of how many features there are, or how we know we got all of them, if that's even the right frame. We think it's quite likely that we're orders of magnitude short, and if we want to get all the features in all layers, we would need to use much more compute than all compute needed to train the underlying models. This won't be tenable. This field must find significantly more efficient algorithms. At the high level, it seems like there are two approaches. The first is to make sparse autoencoders themselves cheaper. Secondly, we might try to make sparse autoencoders more data efficient. All right, shrinkage. We use an L1 activation penalty to encourage sparsity. This approach is well known to have issues with shrinkage, where non-zero activations are systematically underestimated. We believe this significantly harms sparse autoencoder performance, independent of whether we've learned all the features or how much compute we use. Recently, a number of approaches have been suggested for addressing this. Group also unsuccessfully explored using 10H and L1 penalty, which we found improved proxy metrics, but made the resulting feature less well. Interesting pointers to future work. Other major barriers to mechanistic understanding. For the broader mechanistic interpretability agenda to succeed, pulling features out of superposition isn't enough. We need to answer attention superposition, as we expect many attentional features to be packed in superposition across attention heads. We're also increasingly concerned that interference weights from weight superposition may be a major challenge understanding. So let's no idea what this means at the moment. Scaling interpretability, even if we address all of the challenges mentioned above, the sheer number of features and circuits would be challenging in and of themselves, sometimes called the scalability problem. One useful tool in addressing this may be automated interpretability. However, we believe there may be other approaches and limited scientific understanding. While we're pretty persuaded that features and superposition are pragmatically useful theory, it still isn't that tested. At the very least, variants like higher dimensional feature manifolds and superposition seem quite plausible to us. Even if this is true, we have a very limited understanding of superposition. Okay, cool. Let's go back to the beginning. And what should we start with? Scaling dictionary learning for Claude 3 Sonnet. That seems like something good to start with. Assessing ability, computational. Yeah, so let's start with this. Then we'll probably read the intro of this and this. We'll see what this is about. I don't think we'll be looking at a lot of specific features because we don't have that much time. Except I am really curious about the model's representation of self. So let's do that. Our general approach to understanding Claude 3 Sonnet is based on linear representation hypothesis and superposition. Okay, we went through this, right? SAEs were sparse autoencoders. Sure. Our high-level goal is to decompose the activation of a model into interpretable pieces. We do so by training a sparse autoencoder on the model activations as in our prior work, and that of several other groups. Sparse autoencoders are an instance of family of sparse dictionary learning algorithms that seek to decompose data into a weighted sum of sparsely active components. Algorithms seek to decompose data into a weighted sum of sparsely active components. Okay, so dictionary. So right, they have they are treating the model, so Claude 3 Sonnet, as something static. So that's a thing that they're trying to understand. And sparse autoencoders are a thing that create dictionaries of like basically it's compression. They're trying to compress the world using as few sort of pieces of representation as possible. That's why it's sparse. So that's what dictionary learning is. Our SAE consists of two layers. The first layer, the encoder, maps the activity to a higher dimensional layer via learned linear transformation followed by real nonlinearity. We refer to the units of this high-dimensional layer as features. Units of this high-dimensional layer. The second layer, which is the decoder, attempts to reconstruct the model activations via a linear transformation of the feature activations. The model is trained to minimize a combination of reconstruction error and an L1 regularization penalty and feature activations, which incentivizes sparsity. So again, there are two layers. It's kind of confusing that they say encoder and decoder, when this doesn't really have anything to do with transformers, I think. But I guess no, the terminology was there before, so that's fair. So maps the activity to a higher dimensional layer. So there's this fan out. That's linear transformation followed by ReLU. Refer to the units of this high dimensional layer as the features. Okay. Second layer, that's to reconstruct the model activations by a linear transformation of the feature activations. Okay, cool. Once the SAE is trained, it provides us with an approximate decomposition of the model's activations into a linear combination of feature directions. SAE decoder weights with coefficients equal to the feature activations. The sparsity penalty ensures that for many given inputs to the model, a very small fraction of features will have non-zero activations. Thus, for any given token in any given context, the model activations are explained by a small set of active features out of a large pool of possible features. For more motivation explanation of SAE, see the problem setup. And so this looks like something I will need to read. Where's problem setup? Problem setup. There we go. Okay, so this is basically MLP. Okay, let's go back to this. Here's a brief overview of our methodology, which we described in greater detail in Update of Hypertraining SAE. We are probably going to skip that because we care about high-level overview at this point. But this looks like standard deep learning stuff, weights and biases and ReLUs and all that good stuff. So, experiments. Our Cloud3 Sonnet is a proprietary model for both safety and competitive reasons. Some of the decisions in this publication reflect this, such as not reporting the size of the model, leaving units of certain plots, and using a simplified tokenizer. For more information on how Anthropic thinks about safety considerations, blah, blah, blah. In this work, we focus on applying SAEs to residual stream activations halfway through the model, i.e. at the middle layer. We made this choice for several reasons. First, the residual stream is smaller than the MLP layer, making SAE training and inference computationally cheaper. Second, focusing on the residual stream and theory helps us mitigate an issue we call cross-layer superposition. We chose to focus on the middle layer of the model because we reasoned that it is likely to contain interesting abstract features. Okay, so this reminds me again of this content paper where we were starting with really low-level features, and the deeper in the network we went, the higher level the features were. So if we kind of apply the same sort of thinking here, in the middle of the model where we have features that are sort of abstract, but still informative. So they're not like the final answer, but they probably represent some reusable pieces that might be interpretable. Cool. We trained SAEs of various sizes. Million, 4 million, and 32 or 34 million features. The number of training steps for the 34 million feature run. Does that mean? Oh, interesting. So the feature. Okay. The number of training steps for the 34 million feature run was selected using a scaling laws analysis to minimize the training loss given a fixed compute budget. We used an L1 coefficient of 5. We performed a sweep over a narrow range of learning rates suggested by scaling law analysis. We chose the value that gave the lowest loss. Okay, so this is sort of mechanics of how they did this. Okay, not super important right now to understand the gist of the paper. For all three SAEs, the average number of features active on a given token was fewer than 300, and the SAE reconstruction explained at least 65% of the variance of the model activations. At the end of training, we defined dead features as those which were not activated over a sample of 10 to the 7 tokens. The proportion of dead features was roughly 2% for 1 million, 35% for 65% for dead features. Interesting how quickly the number of dead features is increasing. I wonder if maybe it would be worth to, if it would help if we decrease the sparsity encouragement. I guess then things get more expensive. Scaling laws. I think I'll skip this. I mean, this is really relevant if you actually want to implement this to get an idea of what kind of hyperparameters to use. But at the moment, we care about high-level understanding. So let's skip scaling laws for now. Assessing feature interpretability. Let's go over this. In the previous section, we described how we trained a sparse autoencoder on Cloud3. And as predicted by scaling laws, we achieved lower losses by training larger SAEs, but the loss is only a proxy for variation errors, which are interpretable features that explain model behavior. The goal of this section is to investigate whether these features are actually interpretable and explain model behavior. We'll first look at a handful of relatively straightforward features and provide evidence that they're interpretable. Then we'll look at two much more complex features and demonstrate that they track very abstract concepts. We'll close with an experiment using automated interpretability to evaluate a large number of features and compare them to neurons. So at the beginning, when I said that features are kind of like neurons, this is very much not true. What they mean by features here is something else. These are these sort of nodes in this new thing that they trained. For examples of interpretable features, in this subsection, we'll look at a few features and argue that they are genuinely interpretable. Our goal is just to demonstrate that interpretable features exist, leaving strong claims, such as most features being interpretable, to a later section. We will provide evidence that our interpretations are good descriptions of what the features represent and how they function in the network, using analysis similar to that and towards monosemanticity. The feature we study in the sections correspond to the Golden Gate Bridge, brain sciences, monuments and popular tourist attractions, transit infrastructure. Here and elsewhere in the paper, for each feature we show representative examples from the top 20 text inputs in our SAE dataset, as ranked by how strongly they activate that feature. A larger randomly sampled set of activations can be found by clicking on feature ID. Cool. Oh, this is fancy. I really like this interface instead of reading PDFs. Okay, larger, the highlight colors indicate activation strength at each token. Okay, so this feature gets activated around here, and this feature around here. That's interesting. It gets activated here, and not, for example, neuroscience. That's weird. But maybe if there's a word that somewhere else, it will not get activated, so it's only in context. Visit in Egypt, pyramids. All these examples suggest interpretations for each feature. More work needs to be done to establish that our interpretations truly capture behavior function. Cool. It's difficult to rigorously measure the extent to which a concept is present. By the way, if the Golden Gate Bridge has its feature, like Scarlett Johansson probably has a feature, and OpenAI has a feature, and like, how many distinct things could we find? How many features are there? That's really interesting. Examples suggest innovations needs to be also established that interpretations truly capture the behavior and functions of the corresponding features.